Let's unpack this. We're diving into the world of EEG data today,
Hmm.
which, as you probably know, is basically trying to read the brain's electrical signals.
Right.
But analyzing it, well, especially when you're hunting for something like a seizure, it's just incredibly challenging.
Hmm.
Seizures aren't steady, are they? They're dynamic, they change moment to moment, pop up, they're non-stationary events.
Exactly. And that non-stationary nature, that's precisely why a lot of standard analysis methods kind of fall short.
Okay.
They might just miss those really subtle quick spikes or, the specific ways the background brain rhythms shift during a seizure.
Right, like trying to get a whole song just from one beat.
Yeah, or just one instrument's part.
Yeah.
You really need the whole picture, how it all unfolds over time.
And that brings us to our source material today. It introduces a pretty fascinating approach,
Hmm.
this joint time frequency scattering tool, designed specifically for this challenge. So our mission here is to figure out what this tool actually is, how it gives us that deeper look, and why this advanced perspective is so important for spotting those tricky seizure patterns.
The core idea, the breakthrough really, is recognizing you need both.
Hmm.
You need to see how the signal changes over time, that's the time domain, and what frequencies are active at each moment.
Time and frequency.
This tool brings those two views together.
Okay, so we need the when and the what kind of brainwave right now.
Right.
How does it actually do that? This joint analysis, the source mentions a couple of key techniques.
Well, it leans heavily on something called the wavelet scattering transform.
Okay.
Think of it like not just breaking the signal down, but doing it at multiple resolutions or scales all at once.
Like zooming in and out simultaneously?
Sort of like looking super close for tiny details, then backing up to see the bigger shapes, and crucially how those views relate. That's the scattering part, how features interact across different scales.
Ah, so it's grabbing details that simpler methods might just average out or miss entirely.
Precisely. It's really good at catching those quick high-frequency bursts, potential seizure spikes, but also those slower underlying shifts in brain rhythm. You get this much richer, multi-layered view.
Got it. And the frequency part, how does that fit in?
That's where the FFT comes in the fast Fourier transform. It's a classic for figuring out the dominant frequencies.
Right.
So the tool uses FFT alongside the wavelet scattering to paint that full-time frequency picture.
And the way it displays this sounds helpful. The source mentions seeing the raw EEG, maybe in blue, right next to the transform data, maybe red,
Uh,
both on a time chart and a frequency chart.
yes, that side-by-side visual comparison is, well, it's crucial. You can literally see how the scattering transform pulls out characteristics or changes that are way less obvious in the raw signal.
Makes those patterns jump out.
Exactly.
And it's interactive too, which is cool. There's a scale parameter slider. What does tweaking that do?
Adjusting the scale parameter. It's like changing the focus on your wavelet lens. A bigger scale smooths things out more.
Okay.
Makes the broader, slower trends pop, maybe reduces some noise. A smaller scale lets you zoom in on the sharper, more localized features.
So you can experiment.
Right. You play with it to see which scale best reveals those potential seizure patterns in whatever data you're looking at.
That makes sense. Lets you really tailor the analysis. And there's also an input for EEG data length.
Yeah, that's important too. Seizures aren't always just a split-second thing. They can evolve over seconds, minutes sometimes.
Right. They might have a rhythm or pattern.
Exactly. So being able to look at and analyze longer chunks of data helps you spot that kind of sustained activity or periodicity that you definitely miss in just a short clip. Plus, more data means a more robust frequency analysis.
Okay, so pulling this all together,
Right.
what's the big takeaway? What does this let people do that was maybe harder before?
Um, Fundamentally, it provides a much more sophisticated way to look at these really complex non-stationary signals, like EEG during seizures,
A better
a
lens.
much better lens, yeah. By revealing patterns hidden from standard methods, it really boosts the potential for, earlier or more accurate detection. It's super valuable for researchers, students, anyone interested in EEG and neuroscience. It connects the complex theory with something practical.
Yeah, it definitely takes it beyond just spotting spikes. It feels like you're getting at the signal's actual texture, its dynamics.
Hmm.
So here's something to think about. If combining these different perspectives, time, frequency, different scales, can reveal hidden seizure patterns in brainwaves, well, what other complex signals, maybe biological, maybe even things in nature, might be holding secrets that we can only unlock when we look at them through multiple lenses like this, all at the same time?